It's a common belief that a colossal vessel is kept stationary solely by its immense anchor. The popular idea is that its sheer size and weight allow it to burrow into the seafloor. Seems straightforward, doesn't it? Yet that notion is far from the truth. For an enormous vessel, the anchor is merely a point of contact. The genuine principle that halts this behemoth is a fascinating application of physics found within the chain itself. A ship is always contending with the unseen forces of wind and current. To counter them, it employs two main tools. First is the anchor, whose function isn't its mass but its shape, that of a hook. Modern anchors are engineered to grip the ocean floor when a horizontal force is applied. This is most effective in adhesive seabeds like clay or mud. On solid rock or dense seaweed, the anchor simply drags ineffectively. However, even with a perfect grip, the anchor is secondary to the true hero of this story, the chain, formerly known as the rode. This consists of hundreds of meters of incredibly dense steel. A single link has a mass of about 160 kilograms, outweighing a concert piano. While the anchor itself is a substantial 23,000 kilograms, the total mass of the entire chain and anchor can exceed 243,000 kilograms, rivaling a mature blue whale. The true stopping force originates from this collective weight. Here's where the brilliance lies. The anchor isn't simply dropped. The ship deploys a great length of chain, forming a long, weighty curve that rests flat on the ocean floor. This shape is a specific mathematical principle called the catenary curve, and its effect is twofold. Firstly, the immense weight of the chain lying on the seabed generates a tremendous amount of friction, acting like a colossal paperweight. Secondly, and this is the truly clever aspect, the curve serves as an ideal shock absorber. When wind or waves push the vessel, their force is exerted against the chain, not the anchor directly. The energy is spent trying to lift this heavy chain from the bottom. The curve flattens slightly, absorbing the impact like a massive elastic band. By the time any force is transmitted to the anchor, it has been dampened to a mild pull. Without this curve, a powerful gust could easily dislodge the anchor from its hold. So, how is an anchor engineered to stay put ever brought back up? The method isn't to pull, but to propel. The ship uses its engines to navigate directly above the anchor's position. A powerful machine called a windlass then hoists the chain vertically. This upward force ingeniously uses the anchor's shank as a lever to release its grip from the seabed. Captains monitor the length of deployed chain using a simple color-coded system on the links, known as shackles, a robust analog method for managing such incredible forces. This contrasts sharply with Hollywood scenes of battleships executing dramatic, sharp turns using their anchors. This is entirely fictional. In a real-world scenario, the chain would either shatter immediately under the incalculable stress, or the anchor would be pulled from the seafloor and drag ineffectively behind the ship. So, the next time you see a gargantuan vessel floating serenely, understand that it's maintaining a precise equilibrium. It is secured not by brute weight alone, but by an elegant curve, an unseen principle of physics, and the vast, distributed force of its chain.